Hello guys, good morning. Can you hear me? Okay, what have we done last class? Could you tell me? Anyone? Okay, so last class we are done with the location of void in HCP itself. We have seen the tetrahedral voids present at the body diagonal. There are two tetrahedral voids at the body diagonal and one octahedral void at body center, right? Octahedral void are also there at the edge center, right? That we have discussed last class. Okay, yeah. So the next thing we have to discuss here is the ionic crystals. Okay, in covalent and ionic crystal, the difference is that in ionic crystals we have ions, correct? So obviously their size will be different. Means we have cations and anions. So size of anions is more than the size of cations. Okay, so we'll have different radius over there, R plus and R minus. So we have two different radius, but in covalent crystal, all the atoms have the same radius. Okay, but in ionic crystal, we have two different radius. That is the difference between the covalent and ionic we have. The concept is same. Okay, we have to do the same thing in ionic crystals also, right? So let's discuss this one by one. Like there are crystals present here, right? Different types of structures we have. We have rock salt type structures. We have antifluoride, fluoride structure, zinc blende structure, calcium chloride structure, etc. So in all these structures, you should know the position of cations and anions, where the cations and anions are present. Accordingly, we can write down the relation of R plus and R minus. Okay. So in all these structures, 3-4 things are important which they ask in the exam. Okay, whatever exam you write, we'll see those things one by one. Fine. Write down the heading, all of you. Write down the heading ionic crystals. Just a second. Okay. Write on the heading, ionic crystals. Okay, the question that you get in this particular portions, that is based upon the memory, right? You need to know few things about the different crystals, and they'll ask direct questions from that. Okay, write down, in this type of crystal, in this type of crystal, the ions are bonded by the ions are bounded by the electrostatic force of attraction, electrostatic force of attraction. Each ion is surrounded by the largest possible number of oppositely charged ion. And this number is known as, or this number is the coordination number. Coordination number. Okay. So here you see the radius of cation is written as R plus or RC, radius of cation, and the radius of anion is R minus or RA. This is the symbol we use, R plus, R minus, correct? Okay. So for a given coordination number, right, for any given coordination number, the radius of cations, anions are fixed. Radius of cations and anion means what? We have certain size of that particular ion. So when the ions are arranged, right, so we must have some space for that. Like we have atoms are arranged and voids are there, right? Now you replace those atoms by one of the ion, which is usually an anion, right? So atoms are replaced by anions, and voids, in the voids the cations are present in general, not always, in general, because cations are smaller in size, so then they occupy the voids which is present in the crystal. Correct? This arrangement is the arrangement of ionic crystal. We have the positions of cations and anions, how they arrange into that. Correct? So we must require, since we have void, right? So we must have certain size of one particular cation which can be fit into that particular void. Okay? And void, the size of void also depends upon the size of anion. Okay, what is the size of anion we have and their relative arrangement. So obviously we have a certain ratio of cations and anions, that is R plus and R minus. And with that only we'll have the coordination number, right? So for a given coordination number, we have a fixed radius ratio, radius of cation and radius of anion. Okay, so what is that radius ratio? You write it down here. Okay, so write down first of all, here we have a radius ratio. This is coordination number. This is arrangement of ions and examples. So if radius ratio is coming out to be, just a second. Draw this table. Okay. Now, if the radius ratio is 0.155 to 0.225, this is the radius ratio. Its coordination number is 3 and arrangement is planar triangular. Means this is the arrangement of anions around the cations. Okay. Example, we have B2O3. If the radius ratio is 0.2252, 0.414, coordination number is 4, arrangement is tetrahedral. ZNS 0.414 to 0.732. The coordination number is 6, and this is octahedral. NaCl 0.732 to 1. It is 8 and it is cubic arrangement. Okay, body centered, CSCl. Okay, this arrangement is what? It is the arrangement of anions around the cations. Okay. Copy this down. Done? Okay. Right. So this is the thing. So if you see this value, right, this radius ratio, this radius ratio is the radius of cation, that is r plus by r minus. The ratio is this. These values we have, cations and anions. See, all these values are less than 1. It means what? The cations are lesser in size. Obviously, that is true. The radius of the size of r minus is more than to that of r plus. Okay. So for this range, and it happens on its own. Like we have this triangular planar arrangement, means the arrangement is what? If I tell you the first one, the three ions are arranged this way. This is suppose one of the ion we have. This is the another ion. And this is the another one. Right. So all these three ions are what? All these three ions are, you see, the arrangement of anions around the cations, right? So all these three ions are anions, negative. All these three ions are negative. And the void that we have here, it is occupied by the cation, which is this positive, right? So this is the arrangement we have, anions and cations in planar triangle. Okay, if the size range is this, you keep on increasing the size. Okay, if the range falls, if the value falls in this range, then the arrangement around this cation would be tetrahedral. Tetrahedral is what? We have this arrangement, tetrahedral. If you try to understand this, the arrangement is simple here. Means above this three, like this void that you have here, above this you place one more uh, ion, that is cation here, anion here. Above this you place over here one more anion, and then we have the void in between of these four spheres, 1, 2, 3, and 4 on the top. In between there we'll have a void. There the cations is present, and that arrangement is octahedral. So simply if you keep on increasing this range, this radius ratio, the arrangement of the atoms around the cations changes. Okay, so that is called the different geometry we are getting: triangular, tetrahedral, octahedral, and so on. Okay, so what are different types of ionic solids we have and their structures? Okay, next write down the types of structures of ionic solids. Write down the heading, types of the structure of ionic solid. Okay, the first type we have, that is rock salt type structure. Write down. Rock salt type structure. This we also call it as NaCl type. NaCl type. Okay, so we'll see the reference, the example of this type of structures we have. Obviously, we have NaCl because it is NaCl type. So we have NaCl, we have LiCl, we have KBr, AgBr, etc. All these molecules are of NaCl type structure, rock salt type structure. Okay, so we'll see the reference with the reference of NaCl, means whatever the cation of the position of cation we have here in NaCl, means that is of Na plus. That will be for Li plus, K plus, Ag plus, etc. Okay, And the position of Cl minus in NaCl would be the position of Cl minus here, Cl minus here, Br minus here, and Br minus here. Okay. So like I said, in all these structures, there are 3-4 points that you have to memorize. One is how many, like every cation, how many ions or anions surrounded the cation here, right? And how many cations surrounded the anions, that you should know. Okay. You should also know the arrangement, what kind of arrangement we have over here. Okay, so one by one we'll see all this. Okay, so write down in NaCl crystal, all Na plus ions, all Na plus ion, it's surrounded by 6 Cl minus ion and all Cl minus ion, it's surrounded by 6 Na plus ion. Okay, so one Na plus is surrounded by 6 Cl minus. Okay, and 6 Cl and 1 Cl minus is surrounded by 1 Cl minus is also surrounded by 6 Na plus. Correct. Hence the arrangement here, the arrangement we call it as 6:6 arrangement, right? So if I talk about the coordination number of each ion, okay, since Na plus is surrounded by 6 Cl minus, so coordination number of Na plus, each Na plus ion is 6. Coordination number of each Cl minus is also 6, and hence it is, we call it as 6:6 arrangement. This question also they have asked many times in the exam, what kind of arrangement is this? So it is 6:6 arrangement. Another thing, this is the one point you should know. The another thing is, in this particular crystal, NaCl, the anion which is Cl minus, okay, Cl minus has CCP packing, cubic closed packing, and CCP packing is nothing but FCC, face center closed packing. Means what? Whenever we say CCP packing, here I'm writing it down, but after this we won't write it again and again. Whenever it is CCP packing, it means the ions are present at corners plus face center, FCC it is. Okay, so if I ask you the number of Cl minus, effective Cl minus, what is the value here? Number of Cl minus, tell me. Number of Cl minus, you see the contribution of each Cl minus and count the number.
4.
What?
4.
10.
4.
Oh, 4, right. So number of Cl minus, we have CCP packing, correct. So CCP packing means all the corners plus face center. So what we should write? Corners atoms contributes 1/8. So 8 into 1/8. plus we have 6 face center atom, and that contributes half, so it is 4. So number of Cl minus is 4. Okay, this is the information of Cl minus you should have. Another one. Write down Na plus. Write down Na plus ion. It is present in all octahedral void. It is present in all octahedral void. And we know octahedral void are present at body center. So it is present at body center plus edge center. Right? Occupies all OVs, octahedral voids. Okay. So number of Na plus ion, if you count for body center, it is 1. Edge center, we have 12 edges. So 12 into 1 by 4 is the contribution of edge center, and hence it is 4. So we have 4 Na plus and 4 Cl minus effectively. Arrangement of this, if you see, okay. So all these anions, right, it is present like this. Okay, I'm just drawing one face here. You see, this is one face, corner 1. This is just a face where all the corners are occupied by negative ion that I'll write down here. The anions are present over here at the center. 1 negative ions are this, you see, at the center. And this is also the face center, we have Cl minus present. So all these yellow ones are Cl minus. And we know the octahedral void present at the edge center, right? So edge center is this. You see, this is the edge center. This octahedral voids are present, right? And these two are not in contact. You must take care of. Okay, this is the thing we have. These two are not in contact. You must take care of that. Okay, it's difficult to draw this here, right? But this is positive, right? So this green ones are cations. That is Na plus. And Cl minus are this, the yellow one, anions. Okay, so if I ask you what is the edge length, edge length is equals to A, and this should be equals to R minus plus 2R plus R minus. So can I write down this as 2R plus R minus? This is a relation of A and R like we had in covalent compound. But since we have covalent compound, R plus and R minus are equal. So I have written over there what? A is equals to 4R. Right, here we have R plus and R minus. If you see this face diagonal is what? Is root 2A, and this should be equals to 4R minus. Okay, now in this ionic crystal, if they ask you to find out the packing fraction, which they won't ask, so you don't have to think about it much. But here also the concept is exactly the same. The volume occupied by the ions divided by the total volume of the unit cell, correct? So volume occupied by cations is what? There are 4 cations, 4 into 4 by 3 pi R plus Q. There are 4 anions, so 4 into 4 by 3 pi r minus cube divided by a cube. Now you see we have a and r minus relation, r plus r minus and a relation we have, right? So we can easily substitute all these values here and solve this to find out the packing fraction. But you don't have to think about it much. They won't ask you to find out the packing fraction of ionic crystal. But the method is this. Did you understand this? So what all things you should know for all these ionic crystal? You should know the position of cations and anions. You should know the effective number of cations and anions. You should know the coordination number of each cations and anions. And with coordination number, you can easily say what is the arrangement we have. Like in this case, it is 6:6 arrangement. Done. Yes, guys, finished? Okay. Now, the second type of crystal we have, we call it as CsCl type structure, cesium chloride type structure. Okay. Now in this structure also, those 3-4 informations you should have. Okay. So one by one we'll see. Write down this structure has, this crystal has BCC type structure. BCC type structure. Body centered cubic. Okay. Where Cs plus ion present at the body center. Body center. So the number of ions, Cs plus ion, it is only present at body center, so it is 1. Okay. Similarly, if you see Cl minus ion, it is present at all the corners. Okay, so number of ions you see is also equals to 1 by 8 into 8, that is 1. Right? Each Cs plus ion, write down each Cs plus ion it's surrounded by 8 Cl minus ion, and each Cl minus ion it's surrounded by 8 Cs plus ion. Correct? Hence, we call it as it is 8:8 arrangement. Eight is to 8 arrangement. Okay. Again, you have number of this. You can find out the volume occupied by the ions divided by the total volume gives you the packing fraction. But again, I'm telling you, you don't have to count packing fraction. You don't have to calculate packing fraction. They won't ask you to do that. Okay, but the method we have discussed how to do. Okay, done. Okay, copy it down. Okay. Next, you see the third type of structure we have, and we call it as zinc blend. Zinc blend type structure. We also call it as sphalerite type structure. Okay. This ZNS, zinc blend is what? Zinc blend is ZNS. Write down, it exists in two different forms. Two different forms. And that different forms, we call it as zinc blend. One is zinc blend, and other one is wurtzite. Right? Zinc blend and wurtzite. Okay. Write down. The first one you write down into this, A and B, you write down A and B. The zinc blend structure, write down. Zinc blend is, we have CCP or FCC lattice, cubic close packing or face centered cubic close packing, right? FCC lattice. In this, what happens? We have S2 minus ion, right? And ion is this Zn2 plus S2 minus ion. It forms CCP arrangement. And again, CCP arrangement means it is present at the corner and face center. Means corner and the face center. CCP arrangement is this. Okay, Zn plus 2, write down, occupy half of the tetrahedral void. Half of the tetrahedral void. Right? The total tetrahedral void we have 4, because in CCP we have, In CCP, we have 4 is the effective number of atoms. So total tetrahedral void is 8 because one body diagonal have 2. So 4 will have 8 tetrahedral void, and it occupies half of the tetrahedral void. It means what? 4 tetrahedral void are occupied by Zn plus 2. Okay, that is what it means. Next, write down each zinc ion is surrounded by 4 sulfide ion, each zinc ion is surrounded by 4 sulfide ion, and each sulfide ion is surrounded by 4 zinc ion. Hence, what we can say, the coordination number for both ion is 4, and this is 4:4 arrangement. Okay. Okay, this is zinc blend. The first type of structure we have, zinc blend. Now, in this only the second type, you write down Wurtzite structure. So B, you write down Wurtzite. Wurtzite structure. Okay. This one has HCP arrangement, hexagonal close packing. HCP arrangement. S2 minus the sulfide ion forms HCP arrangement. And again, Zn plus 2 occupy half of tetrahedral void. And hence it also has 4:4 arrangement here. Okay, 4:4 arrangement like we have discussed just now. Done? Okay. The next structure we have, write down, that is the fourth type, I guess it is fourth type, and we call it as fluorite structure. Fluorite, fluorite structure. Okay, fluorite structure. Fluorite structures are there in the molecule of type AB2. AB2 type molecule has this kind of structure. Like for example, we have CaF2. This question for fluoride type structure, they have asked many times in the exam. CaF2, we have BaCl2, SrF2, PbF2, etc. All these molecules you see, AB2 type molecules we have. Okay, so what happens in fluoride structure, you see? Write down Ca plus 2 ion, I'm taking for the reference of this CaF2. Okay. CaF2 type you see. Ca2 plus, the cation that we have here. Ca plus 2, it has CCP arrangement. CCP arrangement means the Ca plus 2 ion present at the corner and the face center, right? And each Ca plus 2 ion is surrounded by eight F minus ions. Okay, so the coordination number for Ca2 plus, you see, it is 8. F minus, it occupies all tetrahedral void, all TVs. Okay, all tetrahedral voids, and each F minus is surrounded by four Ca plus 2 ion. And hence it is 8:4 arrangement. Okay, means first we'll write the coordination number of cation and then the coordination number of anion. Right, it is 8:4 arrangement and fluoride structure. This is very important. I've asked questions on this many times in the exam. Just a second. Okay, 8:4. It's very important, fluoride structure. Okay, we have one more structure, that is anti-fluoride structure. Just opposite of this. Anti-fluoride means what? Whatever the position of cation we have here in fluoride, that becomes the position of anion. And the position of anion we have here, that becomes the position of cation. Okay, that is anti-fluoride. Everything will be reversed. This one is 8:4. So anti-fluoride will be 4:8 arrangement. All the things will get reversed. Okay, exactly reversed. So write down the next type we have. Anti-fluoride structure we have in A2B type of crystals. A2B type of crystal. For example, we have Li2O. Example, you see, we have Li2O, we'll have K2O, we'll have Rb2O, etc. All these has anti-fluoride structure. Okay, so here what happens? The anion, that is O2 minus, okay, anion Li2O, suppose we are taking, or Na2O is also very important example of this, Na2O. Okay, so O2 minus that we have here, right? It has CCP arrangement, first of all. Like there we have cation, so here we have anion, CCP arrangement. Means present at all corners and face centers. And each, write down, each O2 minus ion, it's surrounded by surrounded by 8 Na plus ion. 8 Na plus ion, right? Na plus, you see, coordination number is what? Coordination number for this one is 8. Now, when you see for Na plus present at all tetrahedral voids. At all tetrahedral voids, and each Na plus ion, it's surrounded by it's surrounded by 4 O2 minus ion, and hence it has 4:8 arrangement. Okay, so these are the structures we have that you must remember. The position of cations and anions, their coordination number, and what type of arrangement it has, right? So all these things you have to keep in mind. It's very important. Okay, there's one example of covalent crystals. Ionic we have done. Now you see the next one is covalent crystal. One or two examples or structure we have that will go through it. Okay, so write down the heading. We have covalent crystal. Write under this. In this type, the atoms are held together by covalent bond, and the lattice point are occupied by the neutral atoms of same or different type. The lattice points are occupied by the same or different atoms of same or different type you have written. Okay. Oh, right, it is done. Okay, so we have here atom, not ion, because it is covalent crystal. Okay, the most important example for this we have, that is diamond. Okay, so write down the example of it. The structure of diamond, you see. Structure of diamond. Write down. It has, write down, it has FCC structure. It has FCC structure with four atoms that are found to be present in the alternate tetrahedral void. Tetrahedral void means at one body diagonal we have only one tetrahedral void which is occupied by the atoms. Okay, so if you find out the effective number of atoms, that would be FCC arrangement means 8 corners into 1 by 8 plus 6 face center into 1 by 2 plus with 4 atoms that are found to be present in the tetrahedral void. Okay, so we have 4 atoms present in tetrahedral void and their contribution is 1 because it is completely within the unit cell, right? That's why the coordination number or the effective number of atoms here is 8. Okay, coordination number is 8. In this one, you write down next that the carbon atom in tetrahedral void, the carbon atom in tetrahedral voids touches 4 surrounding atoms, hence its coordination number is 4. Okay, next point. Write down. The carbon atom present in tetrahedral void touches the surrounding 4 atoms and hence next line write down 2R is equals to root 3 by 4A. We have the relation of R and A is this. Sometimes they'll give you the radius of the atom and they'll ask you to find out the edge length of the unit cell. So this is the relation we have. Now with this relation, you can easily find out the packing fraction of it. The packing fraction is equals to, we have 8 atoms, so 8 into 4 by 3 pi r cube divided by A cube unit cell volume into 100. So we know the relation of A and R. We can substitute all these value, and the packing fraction is coming out to be 34% approximately. Done? Okay, can we go to the next page? Are you done, guys? Okay. Write down next. The next topic we need to see here is imperfection in solids. In solid. Imperfection in solid. Imperfection is what? Imperfection is nothing but defect. Imperfection is nothing but defect. And what is defect or imperfection? It is the departure from the perfectly ordered arrangement of constituent particles in the crystal. So write down the definition of it. The imperfection or defect, the imperfection or defect the imperfection or defect is the departure from the perfectly ordered arrangement of the constituent particles in the crystal. Right? See, none of the crystals are perfect. All the crystals will have some defect or imperfection. Defect or imperfection is possible in the crystal by the movement of their crystal atoms, okay, from one point to another point, okay, or by the movement of electrons also, or by the presence of some impurities. If all these movement of electrons or atom, if you can freeze this movement, then the solid is said to be perfect, ideal crystal, correct? So write down the next line here. The perfect or ideal crystal, exists at absolute zero temperature. Absolute zero or 0 Kelvin, you write down. Absolute zero, write down like this. Absolute zero temperature or 0 Kelvin. Because the both are the same thing. Either you say 0 Kelvin or you say absolute zero temperature. Okay. Perfect or ideal crystal exists at absolute zero temperature or 0 Kelvin. Next line, imperfection may be intrinsic or extrinsic. Imperfection may be intrinsic or extrinsic. Okay, intrinsic means what? That happens of the atoms which is present in the solid. Like suppose if you heat this, right, then the electron moves from one point to another point within the crystal. That is intrinsic. Okay, extrinsic basically it is because of the presence of impurities. When you add some impurities into this, like for example, if I tell you gemstones, right? Gemstones, it is the crystal of Al2O3, and it is colorless. Gemstone is colorless. Crystal of Al2O3 and gemstone is colorless, right? But if you add impurities into this in gemstones, right? So its color changes, right? From colorless, it becomes colors now. So because it is the color changes because of the impurities, when you add impurities into this. So this is one kind of imperfection because you are adding impurities into this. And what kind of imperfection it is? It is extrinsic imperfection because you are adding something from outside, right? So intrinsic within the metal, extrinsic outside if you add something into it, right? Perfect. Absolute zero temperature is this. Zero temperature is defined as 0 Kelvin or minus 273 degrees Celsius. See, when the temperature is this low, okay, extremely low, then the movement of atoms or electrons freezes. Okay, atoms cannot move from one point to another point. And imperfection causes because of the movement of these particles, whether it is atoms or electrons. When the movement freezes, there is no movement and hence there is no imperfection, right? That's why we say at absolute zero temperature or 0 Kelvin, the ideal crystal we have. Otherwise, we always have some imperfection into the crystal. Okay, that is one thing. Now, this imperfection, depending upon the atoms or electrons, it is again classified into two categories. Are of two types. Are of two types. The first one is electronic imperfection. Electronic imperfection, as the name suggests, this imperfection is because of the movement of electrons. And the second one is atomic imperfection, right? Atomic imperfection, which we also call it as point defect, okay, atomic imperfection. So atomic imperfection is because of the atoms, movement of atoms from one point to another point in the crystal. Electronic imperfection is because of the movement of electrons, okay. In this type, what is the constituent particle we have which moves from one point to another point? Based on that, the imperfection is classified into two categories. The first one is electronic imperfection, okay. So first thing of this, point wise, just you write down. The first point is, this is due to the irregular arrangement of electrons. This is due to the irregular arrangement of electrons. Next point, at 0 Kelvin, absolute zero temperature, at 0 Kelvin, at 0 Kelvin, there is no mobile electrons, free electrons. Mobile electrons means free electrons. At 0 Kelvin, there is no mobile electrons, hence no conduction. Okay, next point. Next point. As temperature increases, as temperature increases, some electrons may occupy the higher energy state, hence shows conduction. Shows conduction. So you see what happens here. The next point here is, suppose we have electron present at this position, right? And when it move on to the another position, right? Suppose it goes over here, right? Suppose this position was A, and from A it goes to B. So what happens in this process? You see, the electrons moves from A to B. So now the electrons are here at the position B, but A, the position A is unoccupied now. It is vacant. See, this is vacant here. This is the vacancy we have, right? Since the electrons has been jumped, right? So this vacancy, this vacant site that is created, we call it as hole. Okay. H-O-L-E. Do not write W-H-O-L-E. This is hole, H-O-L-E. So whenever the electrons moves from one point to another point, in fact, if atoms also moves from one point to another point, right, it leaves some of the space, right? It leaves the original site and goes to the new site. So at the original site, since it's moved on from that particular original site, so that original site will have some hole over there. Vacancy, we call it as, right? Represented by H. So write down the next point. Write down holes creates due to the movement of electrons holes creates due to the movement of electrons next line, these holes and electrons these holes and electrons gives rise to the electronic imperfection, right? Both holes and electrons are responsible for it. Okay, electronic imperfection. For example, you see, example for electronic imperfection, if elements of group 13 mixed with 15, for example, ALP, aluminium phosphorus if you mix, gallium arsenic if you mix, indium bismuth if you mix, all these shows this kind of imperfection, that is electronic imperfection. So group 13 plus 15 element you can have. You can also have group 12 and group 16. That also gives rise to electronic imperfection, ZnS plus CDS, etc. Not plus, ZnS can show, CDS can also show. Okay, these are the examples of this kind of imperfection we have. Okay, electronic imperfection. Now, after this electronic imperfection, the next one we have atomic imperfection, the second type. Write down. This type of defect is observed due to the arrangement of constituent particles when the particles or atoms moves from its original site okay, when the particles or atoms moves from its original site to any other sites or moved out of the crystal, then this kind of imperfection observes. Then this types of imperfection observes. Okay. Now, this kind of imperfection, we have different types. Okay. Like we have defects in stoichiometric crystal, defects in non-stoichiometric crystal. Okay. 3 types of atomic imperfection we have. All these types are not important. Write down first. Okay. 3 types of atomic imperfection. I'll just write down the types. Only 2 are the important one on which they ask question in the exam. That we'll see. Okay. So the first type we have defects in stoichiometric crystal. This is one type. Defect in non-stoichiometric crystal. Non-stoichiometric crystal. Okay. And the last one is line defects or dislocation defects. Okay. Now, defects in stoichiometric crystal. Stoichiometric crystals are those crystals in which cations and anions are exactly in the same ratio as indicated in the molecular formula, right? So this stoichiometric crystal, we have 2 very most important type we have here. This we call it as 2 defect we have here, that is Schottky defect, and the other one we have Schottky defect, other one we have Frankel defect. Just a second. Frenkel, Frankel defect. Okay, these are the 2 different defects. We'll see these 2. Non-stoichiometric crystal, we have metal excess defect. We have metal excess defect. Second one is metal deficiency defect. Metal deficiency defect. As the name suggests, it is, the first one we have more metal ions present. Second one we have metal ion is lesser, right? And third type we have in this, we call it as impurity defects because of the presence of impurities. Okay. So out of all these defects in stoichiometric crystal, Schottky and Frankel are important, on which they have asked question many times. Okay. So we'll see these 2 one by one. Write down. The first one is Schottky defect. Write down in this. This defect is observed. This defect is observed when equal number of cations and anions, when equal number of cations and anions are missing, equal number of cations and anions are missing from their original sites, equal number of cations and anions are missing from their original sites, and the same number of holes have been created. Right? An equal number of holes have been created. Observed in a strong ionic compound. Observed in a strong ionic compound. AB type of molecule. AB type of molecule, we have this kind of defects. NaCl, KCl, KBr, AgBr. AgBr is very important because it is in this structure, both defects is possible. Schottky and defect, Schottky and Frankel, both defect possible in this. Okay. So now this type of defect, you see what happens. Suppose we have a crystal in which different atoms are present. Okay, and if I draw this structure as this, suppose we have A, B, just a second. Suppose the atoms are arranged like this here. Okay. At this junction, suppose the atoms are arranged. We have A here, A, and here we have B. Like this is present. Okay. Now equal number of atoms are missing, correct? Suppose A and B are missing from the sides. Okay. So what happens if this A and if this B is coming out of this lattice, then what happens? We'll have a hole over here. A hole creates like this, you see. This one or this one if it comes out. Right. Then this is the hole created. Right. These are the holes created. Right. Atoms are missing from the original sites. Okay. Equal number of atoms. A and B must be equal. So because of this movement of atoms, the property that is that has been changed in this molecule, this defect, which changes the property of this crystal, we call it a Schottky defect. Okay. Now the few properties of Schottky defects are important. Since equal number of cations and anions are missing, right? Then obviously if ions are going out of the molecule, then mass of the molecule decreases because the atoms are going out. So obviously the density of the crystal decreases. So the effect of Schottky defect is what? Density decreases, right? Disorderness will be more. So entropy increases in this case. Right? So equal number of atoms or cations, anions have been missed from the original sites. Creates a hole. Now the another one is Frankel defect. Write down the heading. Frankel defect. Write down. Okay, write down if some of the ions, in bracket you write down usually cations, if some of the ions in bracket usually cation of the lattice, occupy interstitial sites leaving a corresponding number of normal sites vacant, Next line, it creates vacancy defect. It creates vacancy defect at the original site. It creates vacancy defect at the original sites and interstitial defect at the new site. New site means where it goes. Interstitial defects at the new sites. Example of this type we have is, like I said, AGBR. It shows both type of defect. We have ZNS also possible. AGCL, AGI. Right? In all these molecules, this defects has been observed. The condition for this defect, write down. The condition you write down. The coordination number should be low. Should be low. Should be low. And the size of anion should be bigger than the size of cation. These are the two conditions we have. Size of anion should be bigger than the size of cation. Next point. It is not observed in alkali metal halides. It is not observed in alkali metal halides. Now what happens here, you see, first of all, Okay. Now you see here we have A, oh, I'm sorry. This is the arrangement we have of A and B. Now what happens? Some of the ions loses its original site. Right? So what happens here? From this, suppose if this A moves from this point to any interstitial point, suppose here. From here A comes out and it occupies this position. Right? So this is Frankel defect. Right? This A comes from this original sites and occupy the interstitial sites. It is not coming out of the crystal. It is there in the crystal, but not at the original position. So in this way, we have a hole over here, right here. So since the atoms are not going out of the crystal, right? So its mass won't change, hence no change in density. That is a property of it. Density does not change, right? And next to write down, disorderness increases. So obviously the entropy also increases in this case. Right? So these are the two defects which are very important. Okay, Schottky and Frankel. The other types of defects I have already written. Okay, that you must, if you want, you can go through in the book, but not that important. Okay, next one is okay. Next one, write down Bragg's law. We are doing the last part of this chapter, Bragg's law. The heading you write down. Okay, so Bragg's law, it is used to determine the interplanar spacing. Interplanar spacing. What is interplanar spacing? Suppose we have a crystal and we have a layer structure over here. Right? This is the layered by layered structure we have here. Interplanar spacing. Here we need to find out. Okay. So obviously we have crystal. So we'll have atoms present here. Suppose at this point, this is the center, we have atoms present here like this. So interplanar spacing is this distance actually. The distance between the two layer in a crystal, this is d. So we can find out this d with the help of Bragg's law. Okay, interplanar spacing. Okay. Okay. Now for what we do for this in this Bragg's law, you need to understand two things. That is the interference of the wave, light wave. Okay. Two types of interference we have. One is constructive, other one is destructive. Constructive interference is what? Suppose you have one wave goes like this, right? And another wave which is like this, right? This is the, just a second. We have constructive interference, and destructive interference. So constructive interference is, suppose we have two waves of same phase, like this it is going. Okay, and one more wave we have like this, it is going, right? So phase is same, means you see it starts from this direction, it goes, and this also goes to this direction. So we have same phase of these two waves. But when we have the wave like this, one is going this way and another one is going this way. So these two are said to be in opposite phase. So when the two wave combines of same phase wave combines, then the net wave we have here will have the amplitude, which is the sum of the two wave that we have here. It goes like this. Just a second. Okay, so the net effect of this will be like this one. And suppose its amplitude is A1, this is A2. So here the net amplitude will be A1 plus A2. Just one information you should have to understand this. But if you have two waves like this, opposite phases, then the net wave here will have amplitude lesser than this, depends upon the amplitude of this and this. If they have equal amplitude, then this will be zero. We don't see here any wave, it's a straight line. But this here, the net amplitude A is equals to A1 minus A2. That is what we do. Right, so we'll get here, the amplitude here is lesser than this. Constructive interference gives you more amplitude. Destructive gives you less amplitude of the reaction. Even if the amplitude is same for the both wave here, then we don't observe any wave over here. It will be a straight line because both cancel out each other, right? Now coming back to this point, here we'll conclude what? That constructive interference will have more amplitude, right? Now coming back to this point, okay? See, to find out the interplanar spacing, what we do, we use a light source here, right? We use a light source this side, and from this we'll try to project the light onto this surface, on the surface of this crystal, whatever crystal, we need to find out the interplanar spacing. And this light reflects this way. And here also, from here also it goes this way. Correct? So this side we have, you see here, this side we have source of light. And this side we have detector, which detects the coming light. And with detector only, we'll do further study of this, whatever we detect over here, and then we can find out this D, which is the interplanar spacing. Okay. Now the light that comes over here, you see here, first of all, the path, this is suppose path 1 we have, and this is path 2. So obviously the path 2 is longer, right? Path 2 is longer. And if you see the path difference here, that would be this. If you draw a perpendicular from this point to these two lines, this perpendicular, right? This perpendicular, it is suppose A, this is suppose A, this is B, this is O, and this is C. Okay. So path difference that we have here, you see between the two path A and B, the path difference is OB plus OC. Okay. This angle of incident, this angle here, you see the angle with which this light is coming over here, this angle is theta. And hence this angle is also theta and this angle is also theta. Okay, one thing. Now with this, we know to get this maximum amplitude, if the amplitude is 0, then this detector won't detect anything. Hence, to get this, to have this detection over here, we must have constructive interference here. And for constructive interference, the two wave must be of same phase. So first things for Bragg's law, what we do, we take constructive interference. So this is the one important question. You can ask this question from you, that what interference is required? We required constructive interference for this purpose. That is one thing. That's why we have discussed this. Now, constructive interference means we have the same phase. Same phase means the two wave that comes out from this source, it goes like this. It goes like this. Since constructive interference, so here also the wave must have the same phase, so it will go like this only. Just a second. Go like this only. Okay. And from here, this will come out like this, it goes. Here also it will come out like this, it goes. Because the wave must be what? Of same phase. Obviously should be it is going like this, so it should go like this. Okay. So now this distance OB plus OC, if you try to find out in this triangle, you see triangle, in the triangle, you see in the triangle ABO, if you find out OB, it will be D sine theta. Sine theta is this divided by D, this distance OA is the interplanar spacing D. So OB is D sine theta, and similarly OC, if you find out in the other triangle AOC, it is also D sine theta. So path difference OB plus OC is 2D sine theta. Correct? So now you see this, I'll just make some space here only so that I don't have to go to the next page. This you see, destructive is not required. I'll just remove this. Okay. Now you see this distance, B, OB plus OC. So OB plus OC is this. We have B here, O here, and C here. And similarly, we have like this, B, O, and C. Correct? So at B, the wave is coming from down, correct? You see this? The wave is coming this way at B. And at C, it is going up like this. It means one possibility is what? That this wave will go like this. One possibility is this, come down, and then it will go like this. One possibility is this. And this is one complete wave, right? Wavelength, this distance is lambda. Another possibility is what? If the wave is going this way at B and coming out C at this. So another possibility is it will go this way. Okay, this should also come down a little bit. So this will come down like this. So it is O. So you see here, if you observe this, one last thing here, this distance is one wavelength, and that is lambda. This distance is again lambda, and from here to here, it is again lambda, lambda and lambda. So BC, we have one lambda. Here BC, we have one possibility is this one lambda. Another one is 2 lambda. Similarly, we can have 3 lambda, 4 lambda, 5 lambda, 10 lambda. It means the path difference, that is BC, BC should be equals to the integral multiple of the wavelength. Write down the integral multiple of lambda wavelength, which is nothing but n times lambda, where n is the order of this, which can be 1, 2, 3, and so on. And hence, this Bragg's law, the equation that we get is path difference is n lambda, and which is also equals to 2d sine theta. So Bragg's law, the only one equation we have that you have to memorize, n lambda is equal to 2d sine theta. Okay, so this here, when you know this equation, everything will be given. This theta will be given, n will be given, and they usually write n is the order. So if they write, this is not that reaction order, right? Just they'll give first order crystal is this, second order crystal is this. So n value correspondingly we can write n is equals to 1, 2, and so on. Okay, wavelength will be given, theta will be given. You can find out this d, which is the interplanar spacing. To sum up this, just you need to keep this relation in mind. You can solve all the numerical questions based on this. Another, the theoretical question is what? That the interference must be constructive. Destructive interference we won't have to get the better result. Understood this? Tell me, any doubt? Okay, fine. So fine, so we are done with this chapter. Okay, just let me know what we should start next. What is the next chapter we should start? Let me know, guys. Shall we start solution? Have you done this? Or any organic chapter? Tell me. Solution, right? Is it fine? Okay, fine, we'll start the solution. Do you have any book for reference? Are you following any book for chemistry? What book you have at home? Okay, NCRT you have. Fine. So in NCERT, there is one topic given in solid state, that is magnetic properties. Okay, it's completely theory again. That magnetic properties you revise once, okay, you go through once. Paramagnetic substance and all. Okay, basic definition we have, just go through once. Okay. Yeah. Okay guys, thank you. Take care, bye-bye.